We're moving into Chapter 2, and in Chapter 2, we continue with our discussion of kinematics, but this time we are looking at the motion of objects in 2 dimensions. So in Chapter 1, we were looking at objects traveling along straight lines, either east and west, north and south, or up and down. But now we're going to be able to calculate the motion of objects in 2 dimensions. Before we start, we have to take a moment to look at how to express directions that are not exactly east, west, or north and south. So take a look at this vector here, this directed line segment. This vector here is 20 degrees above the east direction. So we say it is 20 degrees north of east. So if you were to write that direction out, we would say 20 degrees of east. 20 degrees north of the east direction. So we can write 20 degrees north of east like this. Start off with square brackets. In the middle, write your angle, which is 20 degrees. And beside it, to the right, we write north. So this expression here says 20 degrees north. But our principal direction is east. So when we read this, we always start in the middle, and we read 20 degrees north of east. Now we could have also expressed this same vector as a certain amount of degrees east of north. How many degrees east of north would this be? 70. And the reason why is because 70 plus 20 equals 90 degrees. So we write this as 70 degrees east of north. Both of these are equivalent. It doesn't matter which one you write, but you have to understand that they are the same direction. So today, for the first time, we look at how to add non-collinear vectors. And we define non-collinear vectors as vectors that are located along different straight lines. So the way we write or add non-collinear vectors, and this is method number 1, non-collinear vectors are added by a graphic strategy called tail-to-tip. Now you saw this tail-to-tip method. We're going to use the exact same method, but this time we'll use vectors that are not located along the same straight line. So let's try this out with our first example. A cyclist rides her bicycle 50 meters due east and then turns a corner and rides 75 meters due north. What is her total displacement? If we look at what is given in this question, we have displacement 1, which is 50 meters east, and displacement 2, which is 75 meters north. And they want us to find the total displacement. So in order to find the total, as we find any totals in math, we would just have to add up these individual displacements, delta D1 plus delta D2. So that would be 50 meters east and 75 meters north. Since these are vectors and these contain directions, an alarm bell should sound. And you should ask yourself the same two questions we've been asking ourselves. Number one, are they collinear? And the answer to this question in chapter 1 has always been yes. But in chapter 2, for the first time, we see that east and north are non-collinear. They're not pointing in the same straight line direction. So we cannot proceed algebraically. And I'm going to write that down as a warning. You cannot proceed algebraically. You need to use method 1, tail to tip. So when using this graphical strategy, it's important that we establish a scale, one that will allow us to draw these vectors efficiently on our paper. The scale that I want to use is 1 centimeter equals 10 meters. We also have to write down the reference coordinates to show where the direction will be. So we'll have north facing up. And we'll begin by drawing each of these vectors and placing them tail to tip to one another. It doesn't matter which vector you add first, or draw first in this case, because when you add variables together, you can add them in any order and you'll get the same answer. When drawing non-collinear vectors in the graphical strategy, it's important to kind of map out where these vectors are pointing and where they're going to be lying along your page. So in order to do so, the first vector, 50 meters east, I'm going to draw this vector towards the bottom of the page. And I've mapped this out so I know where it's going to end up. So I'm going to draw a vector that is 5 centimeters long, pointing to the east. And I'm going to label this delta D1, 50 meters east. To this vector, I'm going to add the second vector, 75 meters north. And I'm going to place its tail on the tip of the previous vector. So we'll draw a vector that is 7.5 centimeters long, whose tail begins at the tip of the previous vector. And we'll label this delta D2. So we've just added these two vectors tail to tip. We've placed one vector tail to tip to the second vector. Now we haven't found the answer yet. The answer is found by joining a line from the tail of the first vector to the tip of the last. So we have two vectors here. We're going to find the tail of the first vector and the tip of the second vector. And we'll draw a straight line between the tail of the first vector to the tip of the last. And this line here is our answer. So what do I do with this answer? Well, from this diagram, you need to report a magnitude and a direction. So our answer is total displacement, delta D, total is. In order to find the magnitude, you need to measure this with your ruler and convert it using your scale. And you should get a vector that is approximately 9 centimeters long. So that'll translate into a vector that is 90 meters long. So we determine the magnitude by measuring with a ruler and converting using our scale. Now, since these are vectors, we have to report a direction. So if we look at this vector, we say it's pointing somewhere in between north and east. Now we cannot with certainty say that this is northeast. Northeast is a particular direction that occurs 45 degrees east of north or 45 degrees north of east. But we actually have to use our protractor and determine how many degrees north of east or how many degrees east of north this is. So let's try with the east. Place your protractor along the east direction. We'll use east as our principal direction. If you do so, you see that this vector lies 55 degrees to the north of east. So this angle is 55 degrees. Once you've determined the angle, place it in the middle of the square brackets. So we write 55 degrees north of our principal direction where we placed our protractor, which was east. Now we could have also expressed this as some direction east of north. If we line our protractor up against, in this case, the imaginary north line, we see that we end up with a direction that is 35 degrees to the east of north. Both of these are equivalent. Both of these will be accepted on any test or assignment. Some textbooks will say, always choose the one in which you get the smallest angle. So in this case, it would be 35 degrees east of north. But that's not necessary for us in this course. And that's our final answer. The total displacement is 90 degrees, So we can say that the total displacement of this cyclist is 90 meters, 55 degrees north of east. In sample problem number 2, we're really going to test your ability to read these directions for the vectors and make sure that you can draw these diagrams and place these vectors on your page in the correct orientation. The question reads, a squash ball undergoes a displacement of 6.2 meters, 25 degrees south of west, as it approaches a wall. It bounces off the wall and experiences a displacement of 4.8 meters, 25 degrees north of west. The whole motion takes 3.7 seconds. Determine the squash's total displacement and average velocity. So we'll take this question in two parts. In part 1, we will find the squash ball's total displacement. We're given an initial displacement of 6.2 meters, 25 degrees south of west, and an additional displacement 4.8 meters, 25 degrees north of west. We want to find the total displacement So this is 6.2 meters, 25 degrees south of west, plus 4.8 meters, 25 degrees north of west. An alarm should go off as we ask ourselves the same questions we always do. Number one, are they collinear? And the answer is no. These vectors are non-collinear. So they are non-collinear, so we have to use tail to tip. Before we proceed, we need to establish a scale. The scale that I will use is 1 centimeter is 1 meter. We can actually use the scale to draw it efficiently on our paper. Next, we establish where north is on our paper. North is pointing up. And we'll begin by drawing our first vector. But this first vector is not along the east-west line or the north-south line. So we actually have to be careful when we place it on our paper. In order to do so, what I want you to do is I want you to draw in with a dashed line, rough north, south, east, west coordinates. And it's important to make them as square as possible because this will set up the accuracy of your diagram. Ideally, you'd like to perform this on graph paper or a grid. So at the crosshairs, that'll be the tail of our first vector. And our first vector is 6.2 meters, 25 degrees south of west. So our principal direction is west. And in order to draw this, you have to place your protractor along the principal direction, which is west, and measure 25 degrees south. So with my protractor, I locate 25 degrees south. I place a little dot. And this is where I'll draw my first vector. It's going to pass from the origin through this point, which is 25 degrees, and it's going to be 6.2 centimeters long. I'm going to label it delta D1, 6.2 meters, 25 degrees south of west. Just when you come back and review this, you'll remember that this was 25 degrees to the south of west. To this vector, we will add the second vector. Now the second vector, again, is not pointing north or south or east or west, so it's pointing somewhere kind of in between west and north. So when drawing this, we have to be careful as well. At the point, tip of the previous vector, I want you to draw the crosshairs again with a dashed line. And it's at the tip of this previous vector that we will be drawing the tail of the next vector. And this next vector is 25 degrees north of west. So what you need to do is you need to place your protractor along the principal direction. In this case, it's west. And I want you to find 25 degrees north of west. Mark it off with a little tick. So 25 degrees north of west. And it is through this point that we've drawn that we will extend our vector. And this vector is 4.8 centimeters long. I'll label it delta D2. .8 meters, 25 degrees north of west. And just for our own memory here, we went 25 degrees north of our principal direction, west. So we've added the vectors, and it's time to find the sum, or the total. And the total is found by drawing a straight line from the tail of the first vector to the tip of the last vector. So locate the tail of your first vector, which is here, and the tip of your last vector, which is here, and draw a straight line joining these two. Once you've drawn this, it's time to state your answer. And the total displacement, its magnitude can be determined by measuring the length of this vector and converting it using our scale. If you line this up, you should get 10.2 centimeters, which would translate from our scale to 10.2 meters. Now take a look at the direction in which this is pointing. It's not pointing west. It's actually pointing a few degrees south of the west line. And I want you to make sure that you see this. I'll extend the original west line that we've drawn. And you'll see that this vector is actually pointing a few degrees to the south of west. An inaccurately drawn diagram might lead you to think that this is west, but it's not. So in order to report the direction of this vector, we have to find how many degrees to the south of west this is pointing. In order to do so, place your protractor along the principal direction, which is west again, and you'll see that this vector is pointing 3 degrees to the south of the west line. So we will write 3 degrees south of west. Part A is complete as we found the total displacement, 10.2 meters, 3 degrees south of west. In Part B, they ask us to find the velocity that this squash ball undergoes. So we're given the time, which is 3.7 seconds, and we've just determined the displacement, which was 10.2 meters, 3 degrees south of west. To find velocity, we use the equation, displacement over time. If we sub and solve, we get 10.2 meters, 3 degrees south of west, divided by 3.7 seconds. Punch this into our calculator and report the answer to 2 significant digits. We get 2.8 meters per second. Make sure you include the direction 3 degrees south of west.